we can start now. So our speaker today is Michael Wemyss, is the chair of mathematics at the University of Glasgow since 2016. So his interests are mainly in algebraic geometry and its relations between non-commutative and homological algebra, resolution of singularities, and the minimal model. He's also collaborating in the project Capacity Building in Africa via Technology-Driven Research in Algebraic and Arithmetic Geometry with Ballas, that some of you might know. And the idea of this project was to organize computer workshops and computer algebra packages, and also some theoretical workshops. And well, so this whole situation with coronavirus affected everything. Now some of these workshops are being given through Zoom, and I think some of us that are here participated in one of those workshops. And also Michael is co-supervising two PhD students at Makerere University with David Seresi, that is here also with us. So I think now we can start. Yeah, welcome.
Okay, so thank you very much for the invitation. And thanks also to Jared and David for the invitation to speak. It's a great honor to speak here. Unfortunately, I couldn't be in Kampala in May, but I very much hope to be back sometime soon. So today I'm going to be talking about Tits cones, which are due to Jacques Tits, a French mathematician, basically a geometric group theorist. But the applications I'm going to talk about today are much more down towards representation theory and towards algebraic geometry. And somehow the new thing I'm going to try to describe is the word intersection. So Tits cones have been around for a long time, but there's much less work done in describing intersections inside them. And my aim of my talk is to try to convince you that not only are the theorems somehow visually beautiful, like on my first slide, I'm also going to try to convince you that they're important structurally. And that if we want to understand various aspects of three-dimensional algebraic geometry, we're kind of forced to understand pictures like this. And being forced to understand pictures like this is not a bad thing. There are worse pictures in the world. And so I should add also, before I go on to my next slide, this is joint work in a seemingly never-ending project with my long-term collaborator, Osamu Iyama. Okay, so next slide. Okay, so my plan of my talk comes in 3 parts. The first 2 parts are almost entirely independent. And then right at the end, I'll try to explain the connection between the 2 of them. So the first part, I'll introduce ADE Dynkin diagrams and their friends, and try to describe a little bit of the mathematics there. This is mainly combinatorial, and it's an extension of very classical material. And in part 1, somehow the most surprising thing about part 1 is, in fact, this hasn't been discovered before. And then part 2 of the talk is in algebraic geometry. I'll try to describe what a flop is, which is a certain birational surgery. I'll try to do that by pictures and intuition rather than necessarily going into grim technical details. And then at the end, these 2 entirely independent things, I will try to explain actually they are related and give you some of the theorems in the background about why we want to understand them. Okay, and so with that, I can begin part 1. So ADE Dynkin diagrams are ultimately just some graphs. So what is a graph? A graph has got some nodes, which are these circles. And between 2 nodes, some of them are connected by edges. So an edge between 2 nodes is this line. So again, here's a node, and here's a node, and here's an edge between the lines, between the nodes. And so for the purposes of my talk, these are just basically graphs that we're going to study. And so they are important in a variety of different settings. So for example, in Lie theory, and so I believe there was a talk to this seminar a few weeks ago on Lie algebras, and these ADE Dynkin diagrams appear there as a sort of fundamental ingredient in the classification of semi-simple Lie algebras. These ADE Dynkin diagrams also appear in something called Coxeter theory from reflection groups, and they're quite fundamental there. And they also appear in algebraic geometry through something called Kleinian singularities and Mackay correspondence, which I'll talk about a little bit at the end. But today we're just going to view them as graphs. So let me just talk you through a few of the features of ADE Dynkin diagrams. So the first feature is that there's not that many of them, right? So essentially, they come in one of 5 things, but that's a little bit misleading. So the first one is something called type A. And so AN has got n vertices, 1, 2, 3, n minus 1, n. And they're connected in a line. And so in some sense, this is one of the simplest possible graphs. So it's an infinite family, but it's not a particularly complicated infinite family. So Dn is very similar to An. Again, there are n vertices. The subscript is the number of vertices. But the only difference is this extra sort of knobbly bit sticking out at one end. And that's another infinite family. And aside from those 2 infinite families, there are only 3 other examples. There's E6, which has 6 vertices, 1, 2, 3, 4, 5, 6. E7 has 7, and E8 has 8. And so what's new in my talk today is that I'm going to allow myself a little bit extra freedom. And so I'm going to allow myself an arbitrary choice of nodes. And so the nodes that I'm choosing are the red nodes. And so in type A, I've chosen 1, 2, 3 nodes. In type D, I've chosen the single one. In type E6, I've chosen these 2 red nodes. In E7, I've chosen these 3. And E8, I've chosen these 4. But I want to emphasize, you can make your favorite choice. Any choice is possible, and the theory can apply to it. And so again, just to emphasize once more, what is the input to this process? The input is going to be a choice of ADE Dynkin diagrams, of which there's not that many, and then an arbitrary choice of a subset of the nodes, of which there are more. So next slide. Good. And so from this, I'm going to make you do a construction of something called a hyperplane arrangement. So again, what is the input? You're allowed to choose any of these graphs on my last slide, and you're allowed to make your favorite choice of nodes. You can choose empty sets, or you could choose them all, or you could choose anything in between. And so what are we going to do? So there's going to be some pictures on the next slide and the slide after. But basically, the first thing that we're going to do is we're going to associate to this diagram a vector space. And it's just a real vector space. And so if I chose the AN Dynkin diagram, I'm going to have the real vector space R to the N. So n-dimensional vector space. And it's going to be a very formal thing. The basis is just formally going to be given by the nodes. And so if I choose E6, I'm going to be inside R6. If I choose E8, I'm going to be inside R8. So the dimension of the vector space is going to be the dimension or the number of nodes in my graph. And the key thing from Lie theory is that there's additional information inside this vector space called reflecting hyperplanes. And this somehow comes from Coxeter theory. I'll try to visually describe that on the next slide. And so the upshot is, to every Dynkin diagram, we have this thing called a root system, which is literally just a real vector space with a little bit extra data, the reflecting hyperplanes. And this is a very classical object. And the key is that it does not depend on J. It's just an intrinsic feature of the Dynkin diagram. And so the first aim for today is we want something similar. We want something which is kind of a root system, might not be exactly a root system. We want something which is kind of like that, but has this dependency on our choice of vertices. Okay, so the next slide. Here's my artist's impression of what this might look like. So bear in mind, if we're inside if we're doing E8, we're inside R8, which is somewhat difficult to draw. And so I'm just going to draw you a three-dimensional picture because that's easier somehow. So the root system has a basis formally just given by the nodes. So if we've got E8, we're inside R8. And so if you choose some of the nodes, you get some of the basis. And in particular, if you choose some of the nodes, you get a subspace inside the root system. So I can draw this, kind of. And so let's just assume, so I can draw it easier on my slides, that I've chosen two nodes in my Dynkin diagram. And so that means I get a subspace R to the number of choices, R2. And this is my picture of R2, which is like a sheet of paper, which is in gray. And so this sheet of paper lives inside the big root system. And in that root system, there are reflecting hyperplanes, which look something like this. And so these reflecting hyperplanes live in the larger space and they slice the subspace. And so if I draw what that slice looks like, it looks something like that. And so what we do is we intersect these hyperplanes in the large space with our chosen subspace, and we end up with a finite collection of things, and these things are red, the red things, these are called hyperplanes. And so a hyperplane is just a codimension one object. So if you're in R2, a hyperplane is a line. If you're in R3, a hyperplane is a surface. So the picture's R2, so the hyperplanes are lines. So this is very important, so I'm just going to go through this slide once more, just to try to explain, because I'm going to do this again and again, so I just want the visual. So we choose two nodes in your favorite Dynkin diagram. Of course, you can do more. So two nodes gives me R2, which is a sheet of paper. And this sheet of paper lives inside the root system, which is a large object. Inside that root system is this extra information called reflecting hyperplanes. We take those reflecting hyperplanes and we slice or we intersect them with our chosen thing, and we get some object out. And of course, the picture is two-dimensional, but the principle still applies for any subspace. I can take any subspace, I can still intersect. It's harder to draw, it's harder to describe, but I can still do it. Good. And it's written cone J because it depends on J. Good. So I'll give you some examples. So to do this for two nodes, this is going to be my next slide, but for three nodes, we like doing three nodes because we live in R3 and we can draw it very well. And so here is basically the first somehow non-trivial example. And so I choose the Dynkin diagram D4, and I choose three red nodes, so I live inside R3. If I do this intersection business, I end up with the following actually rather beautiful picture. And so there's some features of this picture I just want to talk you through. So this is a hyperplane arrangement. So the green things are the hyperplanes. And they somehow slice this object into things called chambers. And the chambers are just the bits sort of in between the hyperplanes. And so if I take this hyperplane here, this hyperplane here, and this hyperplane here, the chamber is just sort of the region that sort of fills this gap between them. Similarly, if I take this hyperplane, and this hyperplane, the chamber is just this sort of region inside there. And so this happens to have 32 chambers. And so why is that? Well, this is a picture of something called the cuboctahedron. And it's basically you taking a cube, and so I can try to visualize a cube. And so a cube has got 1, 2, 3, 4, 5, 6 sides. And the sides of the cube are these sort of crosses. So that's one side of the cube. And that would be another side of the cube. And that would be another side. And I've locked off the 8 corners. And so I've sort of locked off a corner here. It's actually easier if I could get it to spin, but I couldn't get my latex to quite do that yesterday. And so how many chambers do I get? Well, I get 4 chambers for each face. 4 times 6 is 24. And I get an extra chamber for each locked off corner, so I get 32. So it's quite a nice example. The second example is a little bit more complicated. So if I choose E8, which is this graph here, and I choose the following 3 red vertices, so 3 vertices puts you inside R3, and so we like to draw it. And I think you're going to have to believe me when I say that this has got 192 chambers. Unless you're very good at counting very quickly, that has got 192 chambers. And the key why I put this on the slide is it's still quite complicated. And so the 32 chambers is quite a simple example, it's kind of manageable. But the 192, it's becoming more complicated. And there's 2 take-home messages from this slide. The first is when you do this intersection business, you get things which are actually a little bit more complicated than you might naively expect. And so when you do sort of simple things, you get relatively simple answers. But in general, the complexity is quite high. And the second thing is that neither of these arrangements are what's called as Coxeter. So neither come in the world of Coxeter theory. And so what we've done is we've taken something in root systems, some Coxeter things. We've done an intersection and we've left the world of Coxeter theory. And this is actually one of the reasons why these things aren't studied as perhaps well they should be. Okay, so I got a representative type of theorem on my next slide. So this theorem tells you if you take any 2 nodes in any ADE Dynkin diagram, the question is, what do you get? And the theorem says that you get one of only 5 things. So technically, to talk you through the slide, that you take any collection of nodes in any Dynkin diagram, with precisely 2 of them, then up to changing the slope through the lines, which actually doesn't matter, cone J is one of the following. And so ignore the circles for the moment. They become important in maybe 2 or 3 slides later. So just ignore the circles. And so in this, here there's 1, 2, 3 lines. And if I count the chambers, there's a chamber here between these 2 lines, a chamber there, a chamber there, 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 and there. So this one has got 6 chambers. This one has got 1, 2, 3, 4, 5, 6, 7, 8. This one has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, I think you might have to believe me, depending how fast you are at counting and how good your eyesight is. But this one's got 12 chambers, and this one has got 16. And we have no conceptual understanding for why this is true. So if I was to give you a pattern that went 4, 6, 10, 12, 16, you would notice there's a number missing. The number 14 is missing. And so that just does not occur as an intersection. And again, we have no conceptual understanding for why that's true. It somehow just does. And so this slide, although it's completely combinatorial, it has actually quite big applications to flops in dimension 3, which I might have time to describe right at the end. Okay, so that's somehow the finite story. So what's that story? I start with an ADE Dynkin diagram and a choice, and we construct something which is finite. But if you noticed in my first slide wasn't a finite thing. It had this infinite number of things sort of in this sort of pattern. And so what we want to do, which is slightly better, is to construct the infinite story from which the finite story comes for free. And so this is the world of extended ADE Dynkin diagrams. So let me talk you through the classical theory first, and then I'll put in sort of the new aspects to it after. So here again, I've just listed on this slide the ADE Dynkin diagrams of my previous slides. And again, as in my previous slide, there's still not that many of them. There's this infinite family AN, there's this infinite family DN, and there's only 3 other examples. And so what we're going to do now is we're going to extend these by adding a single node to each of them. And if you haven't seen this before, how you extend is going to seem a little bit strange, but there are very good reasons of where we should add things. Again, if you do lead theory, do Coxeter or algebraic geometry, there are reasons why we do this. But for my talk today, we can just view the following as somehow random facts. So how do I extend? So for AN, I take the AN line, and I add in one more node, and I connect it to the left and the right hand side. And so by doing that, I get a circle. Granted, I haven't drawn it as a circle, but it is ultimately a circle. To get dn, I have to extend it. I have to add in one more. And what I do is I extend it to make it a little bit more symmetric. So I extend it there. For E6, to extend E6, again, I had to add in one more. And just as a human, you might think, well, I'll extend it to make it a little bit more symmetric. That's exactly what you do. E7, you extend it to make it symmetric. That's exactly what you do. E8, all by itself, you just extend it like that. And so, again, there are reasons why we do this, but for my talk today, again, we just view these as graphs. So again, this is a very classical picture. And what's new today is we're going to allow ourselves an arbitrary choice of nodes. And so inside AN, I've chosen the red ones. So red are my chosen nodes. I've chosen 3 for AN tilde, the following for 3, 3, and 5. Again, you can make your favorite choice of nodes. The theory will apply to that. There's one other feature I want to say before I go on, and that is your favorite choice of nodes does not have to include the extended vertex. So here I have chosen the extended vertex, but here I have not chosen the extended vertex. So the theory is completely independent. You can choose literally any subset of nodes inside any extended ADE diagram. And what we're going to do is we're going to play the same game as before. It's just a little bit more complicated. And so this is where the Tits cone of my title comes in. And so again, the inputs, any extended ATE, not so many of those, but now we're allowed any choice of nodes inside this object. More choices. And so there's a standard story that if you want to do something in this infinite game, you just replace the word root system with Tits cone, and you do exactly the same thing. So the Tits cone is a little bit more technical to define, and it's just harder to draw because it's one dimension higher. But basically, it's the same idea. To every ATE extended diagram, there's a vector space. That vector space has some extra information, somehow reflecting type hyperplanes. We have a subspace, we intersect, and we get something infinite. Which is exactly the same story, but now in this infinite thing. And the key take-home message from this slide is that this lives in the real vector space dimension k-1. So if you choose 3 nodes inside an extended Dynkin diagram, you're in R2. Okay, and just for experts, if there are in the audience, I am taking the level just so I can draw the picture. We can do things without taking level, but if you're not an expert, you can ignore that comment. Good, next slide. So I want to show you that these are actually quite beautiful objects. So here we are, the very first example I gave in the slide 2 was that I have this E6 Dynkin diagram with these choices. So in the finite story, I have 2 choices. So I live inside R2 and I get the following finite thing. Now, I can get from here to an extended vertex just by formally sticking one in, right? So I take this choice and I just formally stick a red thing on the top. And I get a choice of 3 objects inside an extended diagram. Now, if you apply my last slide, I get an infinite arrangement inside 3 minus 1, which is R2. So this object gives me a finite thing in R2. This gives me an infinite thing in R2. And the question is, what is that object? So I can overlay the infinite onto the finite. And I get an infinite collection of lines, which is beginning to look a little bit more complicated. And so this is where the circles in my previous slide come in. And so if I now zoom in, if I can do this on Zoom, I don't think I can. It's not me. So if we zoomed in, we pretended, and we zoom in very close around here, and all you can see is the finite story. You get the finite story back. And so the circles around are trying to remind you, actually, you're zooming in for something larger to get the finite story. And the moral of this story, or this slide, is that you might as well just develop the infinite story, because the finite one comes for free. So we might as well work on this good of generality. There's one further thing, take-home message from this slide, is if I go back one. So this finite arrangement has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 chambers. And in classical Coxeter theory, the hyperplane arrangement with 10 chambers does not have an affine version. But this sort of story with choices of Dynkin diagrams means you get some form of affine infinite thing associated to 10 chambers. Okay, good. And so I have one mildly technical slide which I'm going to skip over. There's two questions. One is, how do we calculate this? And what's the somehow theory behind them? And the second question is, what sort of arrangements can arise? So the first one, how to calculate. This is a little bit technical, but just let me talk about it very quickly. So the real key is the following. So in root systems or in Tits cones, the key property, one of the key properties they have is that all the chambers are labeled by some element in a group. And that group is called the Weyl group, or the affine Weyl group. And when you do this intersection business, you leave the world of Coxeter theory, and so that's just no longer true. And one of the main things myself and Yama had to do is we had to replace that labeling by some other labeling. And it turns out the chambers aren't labeled by elements of groups, but they're by pairs of elements of an order of a group and some subset. And it's a little bit delicate as to what pairs are allowed, but it's entirely combinatorial. But the key point is, as soon as you have a labeling and you have two chambers that are beside each other, you can ask questions, well, if the two chambers are beside each other, is there some combinatorial rule to get between the two different labelings? And it's true, there is one. It's a little bit bizarre, the rule, but it exists. And the key point is, the rule, although it's a little bit technical, it's what's allowing us to actually calculate these arrangements and classify them. And the wall crossing rule also has applications to algebraic geometry, which is somehow what it's motivated by. But nonetheless, it's a little bit philosophical. Maybe try to explain like this, that if you want to tile the plane, you have somehow two options. One is to think globally and try to do some very big global tiling. Or the other one is to start very locally with small tiles and build it up gradually, and then you eventually sort of build it up. And so what this wall crossing rule is telling you is you can start anywhere and using relatively simple combinatorics, sort of build up a pattern that takes up the whole plane. So then the question becomes, what sort of arrangements arise from this process? Again, we're still entirely combinatorial. I haven't done anything in representation theory or algebraic geometry, it's entirely combinatorial. And so the theorem is for any choice of 3 nodes in any extended Dynkin diagram. And why am I showing you this theorem? Well, if I choose 3 nodes, I get something in R2, and so I get a tiling of the plane. And tilings of the plane, I mean, that's been known to civilization for millennia. And so this is a really, really nice thing. And so it turns out, if I do this, I get one of the following 16 tilings. Which looks like this. And so I'm going to pause for a moment, partly to reflect the fact that each one of these pictures takes me about a day to take. And so I feel like I should at least pause to sort of show this to people. But also just to pause to sort of see the complexity of the things that arise. So I want to talk you through this slide a little bit. So the first thing to note is that there's actually 15 or 16 different tilings depending on how you count. So this tiling here is actually the same tiling as this tiling here, but there are dots which are a little bit difficult to see in the pictures. And the dots, the Z2 lattice is different for both. So for most purposes, these are the same hyperplane arrangement. And so there's actually only 15. The second thing to point out is that 3 of them are already known. So this one here, well, that's called affine B2. This one here is called affine A2. And this one here is called affine G2. And so even if you're really into these sort of Dynkin type things, there's still 12 new things on this slide that haven't appeared before. And this is one of my favorite results I've ever seen. It's just visually very beautiful. And again, I just want to, before we go on to the next slide, just sort of point out, like some of these are quite similar. So this is the classical G2 example, and these ones are fairly similar to this. I mean, it's not so different. But when you go down to E8 and you start doing things there, you get things which are pretty radically new somehow. And again, the complexity, a little bit like my previous slide, the complexity is that just one level higher than you just might naively expect. And I just like this as humans. We can just stare at these pictures as humans and see patterns that you can't do by necessarily studying abstract mathematics. And so again, just as another sort of thing you can see from this, you can kind of see circles appearing in the, and these circles are the finite arrangement just somehow appearing in different places. And so the same finite arrangement is just somehow translating in a Z2 lattice across the plane. And so you have this kind of finite story, which are the circles, and you have this random stuff in between. And it's just, at first glance, not immediately clear what that random stuff is somehow supposed to be telling us. So that ends the part one of my talk, which is, again, what was the conclusion? So the input was basically an ADE Dynkin diagram or an extended vertex, extended diagram. We're allowed to choose basically what we want in terms of nodes. We do some crazy intersection and we calculate, which ends out to be quite a beautiful hyperplane arrangement. So part two is algebraic geometry, and somehow from my motivations, why I went in and sort of had to work out what these things are. So I'm going to try to explain to you on a single slide on Zoom what is a flop. So it is a birational surgery. So basically, the idea in a flop is that you take a curve. So I'm going to talk about three-dimensional spaces today. You take a curve, you try to sort of cut it out, and you try to glue another curve in its place. That's the idea. Now, if you do topology, there's basically no rules, and you can basically just do stuff like this. But if you do algebraic geometry, there are more rules. And so if you want to do this in algebraic geometry, if you want to cut something out and paste something back in, you have to make sure that the thing you end up with also lives in the world of algebraic geometry. So how do we go about doing that or ensuring that? So we pick a curve inside a threefold. So I'm in three-dimensional space. This is a cartoon picture. The red lines are curves because they're one-dimensional objects. And the blue surface, the blue piece of paper is a surface, and it's ruled inside this threefold. So we choose a curve, which is this red one here. And we try to what's called flop it. And so what we try to do is we first try to understand, can we cut it out? In algebraic geometry, that translates to, can we contract that curve to a point? So I've taken this curve, I've sort of squished it down to a point. And the flop is you try to extract a curve in a slightly different way. And so this curve, I've cut it out, I've sort of glued something back in, but the variety has actually genuinely changed by doing this. So that's the sort of intuition behind what a flop is. The technical definition isn't necessarily going to help, but let me just talk you through roughly how that goes. So this F is what's called a flopping contraction. So you have a curve and you've contracted it to a point. And the flop is, roughly speaking, the answer to the problem. Everything which is negative here translates the proper transform to something which is positive there. And in some sense, that's just trying to tell you, there's one obvious surgery called the identity operation, and you got to make sure you haven't just taken your curve out and just put the identity back in. Something has had to change, and basically there's some negativity property here goes to some positivity. But the technical thing isn't going to help at this stage. It's mainly the intuition behind it. So the setting of my talk today are multi-curve flops. So again, we're in cartoon pictures. Let me explain what this is. So X is this picture here, which is a three-dimensional algebraic variety. And it has two curves in it, two red curves. and those two red curves are contracted to a point. And it's an isomorphism away from that, so nothing else changes. The only thing that changes between X and spec R is that spec R has a point, and this is replaced by two curves. And today I'm going to assume that X is smooth. Morally, I don't like doing this. It's not in any way important, and everything else follows more generally, but you have to tweak the language a bit. So what are we interested in? Why did the last sort of slides, what were motivating them? And so what I've been thinking about for quite some time now is we want to be able to classify these objects. So if you think that flops are the most fundamental birational surgery in dimension 3, it would be nice to have an actual classification of them, like an actual up to isomorphism classification. It would be helpful from a variety of different perspectives, but also it's kind of, yeah, it's a kind of fundamental thing. It would be very nice to have. We're also interested in things called invariants. So if you do these sort of operations, there are numbers associated to them, which might not necessarily classify the objects, but they give you good information. And there's a whole host of curve counting theories. So Gopa-Kumar-Vaff invariants, Godwin theory, Donaldson-Thomas theory, motivic versions thereof, Pand-Harry-Pandy-Thomas theory. There's lots and lots of curve counting theories, and we're interested in being able to calculate what those are. The homological, or the algebra associated with the flops, is somehow all stitched up in something called the derived category. And to the derived category is associated a manifold. And we want to understand what that manifold is. This is called stability conditions. We're interested in groups because we like groups for a variety of different reasons. And we'd like to know what sort of groups can we get from these three-dimensional flopping contractions? What sort of features do they have? How do they relate to the geometry? And my motivation, the reason I exist almost, is I want to know about non-commutative resolutions of R. And the philosophy is very simple. If you understand the non-commutative resolutions of R, you understand the rest somehow almost for free. And so that's why we're interested in non-commutative resolutions. Okay, so that's my sales pitch over. I can go to a little bit more of mathematics. And so the question is, how do you relate this sort of fairly complicated three-dimensional geometry back down to the combinatorics? And this is, I'm going to do again a visual picture. So this is the three-dimensional object that we're studying, the flopping contraction. And the question is, how do you get the combinatorics at the beginning of my talk sort of shoehorned into this picture? So if you're trying to understand a three-dimensional object, one thing which is not, well, it's actually a pretty good idea, is try to reduce the dimension by 1. So if you're in three-dimensional geometry, you try to slice down to 2 dimensions. So let me give you an artist's impression of what that might look like. And so inside this three-dimensional object, I sliced by a piece of paper to get a surface. And that surface is a subspace of this. In algebraic geometry, I'm choosing a generic or some reasonable object. And again, for a reasonable commutative ring, if I slice by a single element, I get a 2-dimensional. And I take this diagram, I what's called form the pullback diagram, which looks like this, which is basically some, again, a slice inside this. And this part of the diagram is 2-dimensional, this part of the diagram is 3-dimensional. And then Miles Reed's general elephant conjecture or theorem in the setum rides to our rescue and tells us that actually we understand what this surface is. This surface is an ADE surface. And so in particular, this is dominated by something called the minimal resolution. By Mackay correspondence, this minimal resolution is just a Dynkin diagram. So let me explain that. And so I have 1, 2, 3, 4 curves. So I have 1, 2, 3, 4 nodes. And I join 2 nodes if the curves intersect. So this curve intersects with this curve, so I draw a line there. This curve intersects with this curve, so I draw a line there. And this curve intersects with this curve, so I draw a line there. And if you look at this and maybe tilt your head sideways, it becomes a D4 Dynkin diagram. And to get from there to there, I just have to tell you which curves to keep. And so this curve and this curve are kept, and so those are the curves. So what's the upshot of this slide? Upshot of the slide is you have some complicated 3-dimensional object. You slice down to 2 dimensions where it's easier. You lose information when you slice. However, what you gain is that you shoehorned in Dynkin combinatorics, and it's exactly the type of combinatorics that are in the first half of my talk. Good, and that's my Dynkin diagram rotated, and my Dynkin diagram rotated. Okay. So next slide. So the upshot is, to every flopping contraction, we get a Dynkin diagram and with some choice of nodes. So it's pair, Dynkin diagram, choice of nodes. And as before, we can do this formal thing that, for example, if we had E6 with these two things, we can just stick in the extended vertex. We did that before. We were just allowed to do that. And so the start of the talk, the left-hand one gives us a finite thing, and the middle of the talk is that this gives us an infinite thing. And the big question is, what do those finite and infinite things have to do with the flopping contraction? Why are they related, and how are they related? And so the answer is they're related on many different levels, so combinatorial to structural, all the way up to what's called stability conditions. So I'm going to describe to you the bottom one, which is just the bijections, and then somehow the more combinatorial version of it. So this boils down to, all in the end, it just all boils down to rings and modules. So we consider the ring R, which is the base of spec R, is the base of my flop in the previous slide. And we want to understand certain modules for this ring. And so what modules are we interested in? And so it depends if we're after the finite story or the infinite story. If we're interested in the finite story, we want to know those modules M, which have this rather strange X vanishing condition. They're called Cohen-Macaulay modules, which furthermore have this rigid condition that X1 MM is 0. And furthermore, they're maximal with respect to this property, so that we can't add in any other module and remain rigid. And so in the lingo of cluster tilting people, this is known as maximal rigid objects in the category of Cohen-Macaulay modules. But again, ultimately, we are just doing modules over a ring satisfying three properties. So I should say straight up, it's not obvious that these things exist. And if they exist, it's not clear that they have any reasonable properties. So if we're interested in the infinite story, we need infinitely many things. And so we need to make the thing a little bit larger. And this is, let me just rattle through this. And so we're interested in what's called maximal modifying modules, which again are just modules over a ring satisfying three properties. And so the first one is called reflexive modules. So I take my module M and I dualize it with respect to R, and I dualize it with respect to R again. I get back the first thing I thought of, namely M. It's modifying, which again has got some technical X vanishing condition, which can be ignored for now. And again, it's maximal with respect to that above property. So what's the take-home message from these two slides is that we're interested in rings and modules. The ring is fixed, and the modules have to satisfy three conditions. And the reason I'm interested in this is that these modules are the building blocks of what's known as non-commutative resolutions. Good. And so I have one slide with a theorem, and then I have to explain the very first picture on my slides. So the main theorem is basically that these things are the same. So you have a flopping contraction, a three-dimensional birational surgery, and by the slicing slide, you get both a finite arrangement and an infinite arrangement. And these maximal rigid modules or objects in this category are in bijection with the chambers of the finite arrangement, and the maximal modifying objects are in bijection with the chambers of the infinite arrangement. And so the chambers in these arrangements are precisely the structure which classifies these types of modules. And in particular, we get a complete classification of non-commutative resolutions in this setting. We know absolutely everything about them, how they behave, and what they look like. So I want to visually try to explain this theorem to you on my last slide, and this links to my first slides, and then I'm done. So in the opening slides, I had the following hyperplane arrangement. And so the main theorem there tells you that the chambers of this arrangement are in bijection with something. So the chambers here are just the triangles, the region between the triangles. And so let me just draw, I want to put a dot in each chamber. And so I put a dot in each chamber. The dots are precisely those maximal modifying modules of the last theorem. And so there's a bijection between chambers and these objects. And so the dots are precisely those objects. Now, the great thing about the hyperplane arrangement is there's more information. Now, you can look at this dot, and you can look at this dot, and you notice that they are beside each other in the hyperplane arrangement. And so if I draw a line between two dots, precisely when the chambers are adjacent, I get that picture there. And there's a homological interpretation of what those lines are, and they're called mutation of modules. And basically, there's two take-home messages of this slide. And the first is that these hyperplane arrangements are something called the exchange graph in the lingo, but to have such highly regular structure is highly unusual. And the second thing is that this is the bijection, and we then begin to just lift that bijection through a sort of series of things up to some more functorial level, and that somehow comes later. But I think that's me for today, so thank you very much for listening. Thank you.